Good afternoon, everybody. This is of a mathematical topic, but you would not be finding any mathematics in that. This would be kind of a survey kind of presentation, and I would stop where I have been working these days. So I'm trying to explain, or I'm trying to see that what is the evolution of error control codes from second generation to 6G, which is yet to exist. So this is the outline of the talk. First, we shall see the introduction. Introduction is going to give a brief picture of error control techniques that are employed in different generations and how there were certain types of code made a game changer in each generation. And second part, we shall discuss slightly more closely because the error control factor has significantly contributed for that generation, and subsequently it has increased in the fifth generation. And we expect many improvement in error control scheme to achieve the goals that are envisaged in the sixth generation. So in the 2G GSM, the main error control coding factor that was convolutional codes, and then there was a hybrid automatic repeat request one, and then the game changer was the introduction of turbo codes, where people were able to achieve the Shannon limit through experimental simulations. So the turbo code contribute mainly the whatever breakthrough that could happen in 3G, where they embedded data transmission along with the voice. And then the next introduction of LDPC codes that made tremendous improvement in the fourth generation, because the hardware implementation of LDPC codes would be, although the simulation performance are similar, considered very almost in par with the turbo code and LDPC codes, but whenever there is a hardware realization, LDPC codes substantially improve their performance, and that is why LDPC codes were introduced in 4G. And then there are another addition of codes, that is polar code, which was an answer for the Shannon's capacity theorem. Analytically, it has been established that specifically in 2008, it has been established that binary symmetric channel, analytically it has been proved that polar code could achieve error capacity. So that was introduced in the fifth generation, and there were some kind of improvement in the hybrid automatic that request part as well. And then this is what we expect. What are the things that could be there in the sixth generation? Because the requirements are so much demanding that we try to see that all these things have to be in place to achieve those requirements. So first, we are seeing that an ML-aided error correction scheme would be there. Then there would be an adaptive algorithms to mitigate errors and adaptive algorithms for the channel estimations. And also they feels that the blockchain concepts as well as quantum error correction, but the quantum error correction part I have completely skipped because my understanding of quantum error correction is very minimal. Then the term they are trying to use, like what we are having, that UMTS, LTE, 5G NR. So here we are trying to see, they are trying to put the word that ultra reliable low latency communication, that is URLLC, would be the abbreviation that going to connect to the sixth generation. So one can see that all this evolution reflects the complexity and the performance demand, along with the services, high speed, and different features of addition of services and this performance improvement. So quickly we would see that what were there in 4G LTE that would be helpful for us to expect, because every year, although you could see that the requirement are substantially higher, and also the technology also should cope up with those demands. And one can see that from this 3G to 4G, it happened that the turbo code, it has been included, and we have an hybrid automatic request. And the turbo code, there are two types of error correction that happens in this scenario. One is the data channel and another is the control channel. So turbo codes were the main main error correction technique that was used in the data channel, both in the uplink and downlink, and turbo code substantially improved the performance. But whereas for the control signal, they have used the tail biting convolutional codes. So tail biting convolutional codes were a simpler technique which has a lesser error correcting capability. So that was in place for the control signal, where the requirement of efficiency or the error correcting capability is not substantial. So both turbo code as well as tail biting convolutional codes were in place in the fourth generation system. And then on the hybrid request part, we have this is the typical convention of hybrid request. Here the conventional hybrid request has been used. So I don't think we require a separate explanation. So yeah, this is what it is. Both downlink and uplink, there were hybrid hybrid automatic requests were made. But when you go to 6G, the main thing, there are a lot of trust was given in the HARQ. I'm saying that we expected to do that in the 6th generation, because we are searching for the incremental retransmission. So that is one factor that we are going to consider, that is expected to be there in 6G, to increase the latency, to increase the latency period, to improve the latency performance. So what I'm saying is that in HARQ is one technique that is there to reduce the latency, and in the 6G, when we reached 6G, one can see that there is another added feature that has to be requested to reduce the latency. So even further, the modulation scheme also has been adapted in the case of 4th generation. Depending on the channel scenario, it switches between different modulation schemes. One can see that if the channel is really not that good, then it goes to QPSK, and then it moves depending on the channel scenario. It also goes to the higher dimensional modulation schemes. So this is also considered to be another type of error correction mechanism, as well as to improve the throughput. So it is trading with the performance along with the channel conditions. So one can see that this is the combination of working mechanism in LTE. One can see that data is processed through turbo code and interleaved, and the turbo code along with the interleaved feature that will be essential for the burst error correction. Then CRC appended, that is specifically for the HARQ request. Then this is the procedure that has been followed in this is the small conclusion for this. So error correction in this 4G LTE, it is a multi-layered process involving this turbo code, HARQ and adaptive modulation scheme. So one can see that it has been tremendously changed when we come to the 5th generation technique. So that is what we are going to see next. So the key error correction techniques in 5G new radio is, as I said, the game changer was LDPC code, and slightly modified HARQ request has been employed. So these mechanisms work in tandem to detect as well as correct errors to achieve this robust communication of uplink and downlink data transmission. So in LDPC coding in 5G NR, one can see that it has an excellent error correction, specifically in the large data block, and it employs iterative code, iterative decoding. In fact, in turbo decoding is iterative decoding. If you do the simulation, in fact, in the higher block side, turbo code and the LDPC codes have the similar performances. Nevertheless, as I said, in the hardware implementation, these LDPC codes have a better performance, and LDPC also has a feature of this flexible coding rate. Depending on the improvement of the channel, it can employ a flexible coding rate, so that again the throughput and the performance can be balanced. And another part of 5G is the introduction of polar code for the control channel. So the control channel, as I said, the control channel is not as significant as like the data channel. So here for the control channel, earlier also we have used, we could see that they have used the simpler coding technique. So here the polar code is in place. Polar code also, as I said, it is also analytically proved. It's an analytically proved code which achieves Shannon capacity. And here the advantage is that in the control channels are essentially the block length would be much simpler, much smaller. So being it is smaller block length, polar code would be very efficient, because in a smaller block length, polar code outperform LDPC codes in certain scenarios. So that is why it has been used, polar code. So what is this? What you could see in the coding theory perspective, the difference is that unlike in the 4th generation, the 5th generation, both the codes are Shannon limit achieving codes. One is simulation by, it is validated by simulation. The other one is experimentally established. And here also we would be able to have flexible code rates depending on the channel conditions. So we are, the evolution of these codes are very clear now. And this HARQ follows similar strategy. Error detection, then retransmission. Here it has been introduced the incremental redundancy. That will essentially coin for an incremental retransmission. So this will, in 5G, it is in a minimal sense. In the 5G, it will be used only some kind of additional packets or additional data will be provided. But in the case of 6G, there a lot of thrust has been given. At least people are suggesting to address this incremental redundancy, because the coin word that is going to connect with 6th generation is that ultra, that word it will repeat. So that low latency part, ultra low latency and reliable transmission. So in that case, that ultra low latency, this incremental redundancy would be the one of the important factor that has to be embedded with HARQ. So this is the summary of forward error correction in 5G NER. So you can see that LDPC codes were used for data transmission and polar codes were employed in this control channel. So this provides very reliable communication across different 5G scenario. And here also we are trying to employ the different modulation coding strategy to achieve the balance between throughput and error performance. So in the it goes from QPSK to 256 QAM, and we have a adaptive modulation and coding scheme in place. And these are the other enhancement that was there. I should have quickly pointed out the beamforming in MIMO. The MIMO part is also there in 5G, but it does not come in the purview of error control. But this part is also, complements or contribute to the error correcting capability of the system. So the interleaving part, of course, because turbo code has an inherent interleaver associated with, but in LDPC codes also there would be an interleaving. We have to separate, an interleaver has to be placed, and using this interleaver we will address the burst error, and the beamforming will help us to have this kind of quality signal and all. So this is the summary of error control code in 5G NR. You could see that LDPC codes, then HARK, then modulation, this modulation, adaptive modulations and interleaving, and that helps the spread across the transmitted data and efficient transmission in 5G NR. Now this is what we are considering. This is the point of talk. What are the things we expect in 6G? This I have gone through from literature. Some literature suggested these are the main topics. There were many different topics, but I picked which are the intersections of different papers and books. So one is this word comes repeatedly, that is ultra reliable low latency communication, and it is expected to connect with 6G like UMTS, LTE. So like that, already some authors have connected this. Then this massive machine type communication, then this EMBB. So these are the expected features of 6G. To address this 6G, to achieve these features, what are the things that we could have in the error control part. That is what we are going to look in this talk. So the key error correction strategies, there are also some kind of caveat. See, what I'm saying is that this I have taken which I could handle. There are, if you see that there are 10 such points, 10 bullets are there. But I have taken some intersections and some papers and some books. This is the main thing that I could glean from all those collections. One is we expect to improve the performance of the existing forward error correction scheme and robust this hybrid ARQ and ML aided error correction. Then the feature that is have a tremendous significance would be the distributed and cooperative error correction, and then fountain codes for massive IoT networks. That also I will quickly touch. One more factor which could have been included is that this non-orthogonal multiplexing, that also caters some kind of error correction. Connecting this non-orthogonal multiplexing along with the error correction performs excellently well. So that results also could have been added here. Anyway, we shall proceed with whatever it has been presented here now. So in the first case, we expect to improve the performance of polar code. One is the decoding strategy. We shall try to get the list decoding associated with that, or message passing or belief propagation associated with the successive cancellation. That is one particular aspect people are trying to see that. And also it will try to understand that how we could change the different mobility scenario. These kind of codes can be adapted. So this is one part. I mean, what I'm saying is that these are the features that we have to, that has been identified to modify the implementation strategy of polar code to achieve the envisaged requirements. So here one could see that the mobility scenario, how to achieve, because the control channels and the adaptive networks, we can have a flexible coding rate. And one could see that unlike 3G to 4G or 4G to 5G, we are not expecting another new codes that has to be added. Now, if you see that from 3G to 4G, we have added LDPC codes. From 4G to 5G, we have added polar codes. But now we are not expecting any other new codes that to be in. Of course, there is another code, but that's not with respect to the main data transmission site. So that also we would be seeing here. Now, we should have a very kind of the optimized power consumption strategies. And also, we are expecting that some hybrid coding scheme in which the polar code will be connected with Reed-Solomon code or certain type of code, or even further, the more generalized polar codes, such as Reed-Muller codes and how to Reed-Muller codes to be connected. And this is another implementation strategy that has to be considered. That is how we can shorten and puncture the polar code depending on the network conditions. And these are the enhancement that has been expected to be in the case of LDPC codes. Here we would try to have a low latency and real-time, the performance for the short and medium block size of LDPC, because still the LDPC decoding is time consuming. So how to improve that? Second one is that machine learning integration with that. The rate compatible LDPC codes depending on the network conditions. The rate compatible LDPC codes, there are already existing works are there. And this protograph designed LDPC codes, one of the main contenders for the rate compatible LDPC codes. There are other techniques as well. And there is also a proposal like this joint source channel coding, in which both the source coding and the channel coding would be considered together along with the LDPC codes, and scalable and distributed decoding, in which we would try to decode. It's not like considering the entire graph. We would try to break the graph in the module by base, and accordingly we will try to address the decoding part. So and also this has been suggested with these risks. So this is the summary of polar code and LDPC codes that could be there in 6G. I mean, polar code will be mainly focused on the latency part, and LDPC codes will be mostly connected with the massive connectivity. And both the cases we will try to explore the feasibility of faster decoding algorithms. And again, the block length is one of the important parameter. There could be an adaptive block length we have to consider. So each time how to improve the performance with a different range of block length is also one of the important problem here. And this is the second part. I mean, what I would like to emphasize that we are trying to expect to be giving importance that robust HARQ. Here we will try to address how to minimize the retransmission delays. In the HARQ part, how to reduce the minimization of retransmission delay, and also how to bring the shorter feedback loops. I mean, earlier there was only like one centralized server to be there, but how there could be a distributed thing so that we could have a shorter feedback loops to address the this retransmission request. And this adaptive HARQ mechanism, I mean, one is real-time adaptation where the retransmission dynamically based, and then this context-aware HARQ. Here we expect that this machine learning technique will help to predict the channel condition and improve the low latency. Of course, we are all like professing. I mean, these are all things that we are expecting to be there. And also, we have to have a reduced power consumption, and it also should be optimized based on the redundancy, because it should reduce, I mean, multiple retransmission should be reduced. Again, to conserve the energy part as well. And this is one part, how we can integrate between the physical layer and MAC layer, so that that will help to achieve the efficiency and throughput. And also HARQ will try to address this joint source channel coding integration. And also we'll try to have this multiple connectivity and distributed HARQ, where multiple stations will address the retransmission part. And this cooperative, some data, some network, some already connected users can make a retransmission request in between, so that we can improve the signal reliability. And yeah, this is what about the HARQ part. Now we are going to talk about the ML aided error correction. So here I will stop for a while. So what are the things we are presently considering, that mainly about the LDPC codes part. First is that we are trying to see that how to have a multi-layered LDPC codes. In place of a parity check matrix, we may have to consider a parity check tensor, and how to model that. That is one part of addressing. Second is that a non-binary LDPC codes would be an ideal contender for this error correcting capability. At least I feel so, because the non-binary LDPC codes, the main bottleneck of LDPC decoding is the error floor or the trapping set. And as you know that non-binary LDPC codes, the trapping set, almost the probability of having a trapping set is almost, it's very, very small. It's very small. There is a specific condition to happen, then only the trapping set property will emerge. So that way, the main bottleneck of LDPC codes, that is the error floor, that can be addressed using this non-binary LDPC codes. So this is one of the area which we are focusing. And now we shall start with the ML aided error correction. So here we will try to make one of the, depending on the scenario, there would be a bank of error control scheme and different parameters for different error control scheme. And depending on the scenario, the system will learn, and it will switch the optimal coding strategy with a particular type of parameter. So this also, our purpose is to reduce the latency and increase the reliability. And it also will try to learn the historical data, and it would identify the proper error correction mechanism, and it will try to improve based on this present understanding, it will try to predict what would be the better technique that is for the next transmission. So here these are the requirement that is there for ML aided. So we required, this would be the advantage, error correction strategy and efficiency in communication, the reduction in the transmission, and it also will involve the reinforcement learning for HARQ. So as I told, HARQ is the one of the important thing that we are going to address in 5G. And one is the adaptive retransmission. So based on the, may not be transmitting the entire packet, depending on the type of error, it will try to learn that what particular packet or what particular data has to be retransmitted. And it also try to have this context aware HARQ. It would be based on certain type of decision. It would be able to decide itself, the transmitter itself, that what type of packet it has to be resent. And it also, what are the things we have seen everywhere, we will try to see how the ML can be helpful. So here also we will try to see that in the joint source channel coding, how the ML can be helped. And based on that, since the source is also jointly encoded, then the content-based error correction is also another aspect. The content-based error correction, you can see that whenever there is a network, the convolutional code is an ideal place where the content-based error correction, unlike the block codes, the error pattern matters. The error pattern matters. All the graph codes, the error pattern matters, unlike the block code. So here also we shall try to see that how the ML would be even more powerful to address those type of data. And also, somebody has suggested, one particular paper has been even suggested that ML aided error decoding or ML aided decoding would circumvent the problem of this error flow, which I couldn't understand well because the details were missing. Just had a cursory remark that it is expected that ML aided decoding would try to solve the problem of this error flow in LDPC codes or even a graph code, which is not very clear, but that is why I didn't include here. And of course, this is a very expected thing, that channel prediction and noise estimation in the ML aided thing. And as it can be seen that it will predict the noise and characteristic, and hence the performance can be improved. And this is also another aspect that has been given, that in the massive MIMO or massive MIMO system, it will have improved signal detection and interference mitigation between antennas and all. So these are all expected in an ML-aided communication. And this is the summary of ML-aided error correction in 6G, that we try to revolutionize the traditional communication system, introducing intelligence in the error detection and correction process. The intelligence part, as far as I understand, the error pattern they are trying to address, because certain type of error patterns, specifically it is not correctable in the case of an LDPC code. So ML could be one of the ideal candidate to correct those errors. And it also sends the dynamic of the network scenario, and based on that, it will try to improve the performance. And this is what the neural decoders, the channel prediction part, but it is not very much connected to the error control port. But these are also an important factor that is going to improve the performance of the error correction and ultimately achieving the goal of ultra reliable low latency network. Now, this is the added feature of, like as I told, in the case of 3G to 4G, 4G to 5G, there is an addition of error control mechanism. But this was a more important factor that is going to be added in the 6G scenario, that is distributed and cooperative error correction. So this is something like very, very demanding requirement. I don't know how much it could be able to implement now. One is the edge computing that is reasonably now addressed, where the central server, the performance requirement will not reach to the central server. In the locally, it will be addressed. That is one part. Then the peer-to-peer error correction. So the multiple users, they themselves, if the users are correct, one user got the correct packet, so it will try to compare and that itself try to correct the error. They will do the error correction in between. Then there would be a distributive LDPC codes. In the distributed LDPC codes, the different nodes, different check nodes will be corrected the errors separately. And first, this would be a big breakthrough how it has to be achieved in the case of a distributed LDPC codes. And the collaboration of multiple nodes individually correct the process rather than in the holistic scenario which it happens now. So that is one thing that is expected. Then there would be a cooperative error correction. In that case, cooperative relaying, and one is that network coding is also another contender for the error correction. Then the cluster-based error correction is that certain type of channel scenario, it can be expected that some users would be deeply affected. Then there would be a separate measure to address those type of users. So marking a cluster and addressing the error correction in that. Now this is another aspect that has been there in the case of massive IoT network. This is a rateless code. The advantage is that you don't require a HAR queue. Retransmission is not required, and this is also very easy to adapt, scalability and high-speed data. The main advantage is that you don't require a feedback mechanism, and it will use an efficient bandwidth, and as I said, it will be very resilient on the packet loss part. But the problem is that the disadvantage is that the highly decoding complexity, and it requires a extreme energy consumption. So these are the two factors that is there in the fountain codes. So this is the conclusion that I have written, that this has a greater benefit, but at the expense of extremely decoding, the complex decode, and it would be very demanding to integrate with the 6G network. So this is the very brief picture of error control mechanism in 6G. One is an enhanced forward error correction and hybrid automatic requests that was there in 3G, 4G, 5G. But we required one more aspect, that is machine learning aspect combined with all these. Then the quantum error correction, that is also people suggest. Distributed strategy, that as I told, for the error correction. And it should be able to handle different scenario like IoT with limited power, and we required an ultra reliable low latency communication with a critical infrastructure. And the main factor that we are trying to see that the flexibility and these are all the requirement that is there for the next generation services. I will try to make a question of note that has come to me when I come across with another paper, that was modulation classification, ML-aided modulation classification. So ML-aided modulation classification is the ideal aspect of communication technique where the ML can be used. But there is a recent paper that is there by Chad Sooner, and it has been questioned that the work that has been done with a particular data set is not very helpful for other general scenario. Whereas the point here I want to emphasize is that even the modulation classification, which is considered to be very close to ML-aided classification like image processing, many of the modulation classification tools involves the earlier classical modulation classification tool uses image processing classifications, where they use the higher order statistics, and they are able to do that. But then the machine learning part came, and machine learning, the performance was very improved, but it all turned out to be upside down when they realized that the particular data set only those concepts are working. So I have an apprehension about this ML strategy to apply, because I'm not sure that how much it will be independent of the data set. Whatever the features that has been enumerated, how much we could make independent of the data set after its learning is also a very important thing that one has to ponder. So based on that, I will wind up. These are all these things, and these are some references, but there are some more references which I have not included. Mainly I was relying on the first and second one, but there are others also. Thank you very much.
Long live India and France friendship.